Daron, please
Thank
go
you,
ahead.
Marina. Thank you, Navin, for inviting me. It's a great pleasure to be here and joining you, albeit via Zoom. I must say, I'm getting used to this Zoom technology, so it's going to be harder to get motivated to travel halfway around the world when the technology is working, but there are many parts of the human interaction that we're missing, of course. So, but in any case, it's a true pleasure to be here, and I'm going to be talking about joint work with Ali Makhdoumi, Azarak Malekian, and Asu Özdaglar, and Ali and Azarak are here and can answer these questions. I think the topic needs little introduction. Data transactions of some form, either voluntary or involuntary, paid in kind or via monetary means, are extremely ubiquitous, and some forecast that more than half of the economy in the coming decades is going to be data-based, with IoT and various different other online platforms and goods and services becoming ubiquitous. This sort of raises twin questions about what's the right framework for thinking about data transactions, and also about whether we're becoming better off, perhaps hugely better off, as some are claiming, because we have so many data transactions coming from billions of people around the world. And what's the downside? At some level, this might appear an empirical question. Why do theory on this? But actually, what we're going to argue is that the biggest problem here, we don't have a good conceptual framework for answering this question. Many studies that look at the benefits of data start with a general presumption and models that only have the benefits of data. For example, we collect data and then we generate externalities, we can do better innovation, etc. And then when asked about, what about potential costs, they will appeal to some empirical studies, such as work based on survey by Athey and al., that privacy concerns are not that big because people don't pay or don't appear to be willing to pay that much for protecting their privacy. Now, I'm going to argue that neither of these sort of presumptions are necessarily compelling, hence the need for thinking about more of a conceptual framework. And in particular, the main idea here that we are going to be pushing in this work is that data sharing by one users, when it reveals relevant data about others, creates a twin positive and negative effect. The positive effect is the one that most of us know and understand: data is useful for others. But by the same token, when my data is useful about others, that also creates a negative impact on me. And that's because anything that I want to hide or don't want to be known is also being part of the pool. And this is, as I'm going to argue, it goes way beyond anonymity and just ways of anonymizing, or but just people identifying me. It goes well beyond that, in a sense that I'm going to try to argue. So ways of anonymizing data are not going to be sufficient. Moreover, I'm going to argue in this talk, using the model and some other arguments, that the value of information is generally going to be submodular. So when there are data externalities, they're also going to depress prices, so that you cannot just learn about the social consequences of data transactions by looking at what people are willing to accept or pay for data. So negative externalities from data may be substantial, and they can create the calculus of data, at least in some areas. And these data externalities cannot be measured from observed prices, hence the need for more conceptual work. So in a model of this sort that tries to clarify these ideas, we're going to show how to do general competitive and non-competitive analysis, or more competitive analysis, monopoly platform, and then competition between platforms. Let me just give two more slides of what we mean by data externalities, and then I'll jump into an example and then into the model. So in practice, there are going to be two relevant types of externalities from data. And in our model, we're going to pool the two together. One might want to separate them. One is direct information. A post on Facebook, for example, or general online activity will reveal information about my friends and acquaintances. And that information can be used. That's the direct information that Cambridge Analytica, for example, exploited from 270,000 Facebook users from this is your digital app life, and then got information about 50 million users on top of it, which it was able to successfully exploit for electioneering reasons. Even this cannot be just solved by anonymization. Even if the 50 million people were anonymized in some way, the information that I provided that Cambridge Analytica used would have been survived. So again, I want to emphasize here, and I'll come back to this at the end, that this is not about anonymization. The second, I think, is actually deeper, and not everybody may agree this is a negative externality, but in our minds it is. Predictive information necessarily creates a negative externality, or any sort of a potential negative externality. So users' behavior and data are going to enable platforms to predict the behavior of users, the behavior and preferences of other users with similar characteristics. So for example, I can try to say, what's the favorite restaurants of people from El Salvador in a particular age range with particular religious, sexual, social preferences that live in Boston? So once I do that, I'm really gathering a lot of data about specific types of individuals without having any consent or participation on them. And again, anonymization has got nothing to do with it, because I'm not often using that data about the people who provided the data, but for other people who have the same demographic characteristics that may not even be on my online medium. So those are some of the issues that we have to think about. Now, at the expense of making the model that will come in a second trivial, let me give you an example. This is really a trivial example, but hopefully it will fix some of the notation and the idea. So imagine a network of two individuals, users 1 and 2. Each has some personal data that is correlated with others. So in the main model that I'm going to present, which I will later generalize, we'll assume those are normally distributed. For now, it doesn't really matter so much. But let me just capture the dependence of one individual's data on the others with a correlation coefficient, which is rho. So imagine, as we're going to do in the model, that the platform would like to predict the user type, and users value their privacy either for non-instrumental reasons, they don't like information about them being known, or for instrumental reasons, they don't want to use the consumer surplus they're going to get if that information wasn't available to sellers. And let this utility be denoted by VI per unit of information. I'm being loose about what that unit of information is, and I'll be more specific about that in a second. But let that be VI, and normalize the valuation of the platform to 1. Suppose V1 is less than 1, which means that even if user 1 values her information, she still can be convinced by the platform to share, because the platform has better use for that data. But now let's look at the situation for individual 2. So that's, suppose for the sake of this example, that V2 is greater than 1. So actually, this individual is going to get a lot of surplus, or is going to lose her privacy. So she doesn't want her information being known by the platform. And rho is positive. So now the moment individual 1 shares her data, she's going to reveal information about individual 2, which is the negative externality. But more importantly, let's look at the supermodularity, or the depression effect on prices. To do that, let me take the extreme case. This is not needed, but makes it simple for this example. Let's take rho to be equal to 1. Then essentially individual 1 will reveal pretty much everything there is worth knowing about individual 2. And if V2 is sufficiently large, then this is really bad because of the data externality on user 2. But even more importantly, once rho is equal to 1 and we know everything about individual 2, individual 2 has no reason for protecting her data anymore. Even though she has a very high privacy value, once I have revealed everything about her, then she might say, well, I might as well sell my data. But what that happens is that, a la standard Bertrand intuition, now individual 2 and individual 1 are competing with each other to sell their data, and that's going to push data prices down, in this example, to 0. So even if V2 is very high, and V1 can be very high as well, the platform can buy both users' data at 0 price, which has both bad welfare consequences, and prices are going to be completely non-reflective of the value of this data. So now let me say that we are not the first ones to think about this. So there are a couple of papers from 2010 to today that have pointed out the data externalities, and including simultaneous independent work by Bergman, Bonatti, and Tan. But I think our framework is different, more general, and most importantly, I think from my point of view, I think the submodularity role and the effects of this on prices are the specific focus of ours and not others. All right, so for the remainder of the talk, I'm going to talk about model first, then equilibrium with a monopoly platform, and I will talk about equilibrium and inefficiency with competing platforms. Incomplete information I will skip, and I'll spend a few minutes on regulation and policy at the end. I'll also, while in the context of monopoly, I will provide a significant generalization of the framework as well, briefly, just to show you that the functional form assumptions that I'll use at first don't matter too much. Okay, so here is the model. You can focus on the graph at the bottom of the slide, which gives a pictorial representation. Each node in this network is an individual user. Each user has a data which has which is denoted by SI, which consists of XI, which is the useful part of data, plus ZI, which is some normally standard normal. The fact that its variance is normalized to 1 doesn't really matter. That's additional noise. Now the key, that's where the network comes in. The users have correlated data. My data is useful about you either because of the predictive role of information that I've outlined in the introduction or because of the direct sharing. Sigma II is the variance, which varies across individuals. They may have more information, more variable data information. And sigma ij is going to be the correlation between two users, I and j. The key here is going to be AI, which is whether the individual shares her data. And use standard notation. A is the vector of sharing decisions, and S subscript A is platform's data, is the data of all of the users that have decided to share. Now, as I said, we're going to start with a normally distributed setup, and there the following definition makes a lot of sense. And again, I'm going to generalize this in a second. So we think that both the users and the platform think about what we call leaked information, which is the reduction in the mean square error of the best estimator that the platform can use about the type of user I. So I'm trying to predict your type, which is your X1, let's say if you're user 1. If I have no information, that will have a mean square error of sigma 1 square. Now, any information I get is going to reduce that mean square error. And in particular, if I can get a lot of information from other users who are correlated with you, I can reduce that by quite a lot. And that's going to be our measures of leaked information. What do other users do, or sometimes what you do, enables me to get a better prediction of your type, which I can then use for providing different goods and services or capturing or consumer surplus, etc. So the payoffs are all defined in terms of leaked information. So the payoff of the platform is the sum of all of the leaked information minus the payments that the platform makes. Again, these payments could be direct payments, or it could be free in-kind transferred goods and services that the platform makes in return to capture your data, like the same way that Facebook or Amazon would do. The payoff of user I then is going to be, if she shares her data, she gets the payment PI minus VI, which is her value of privacy, minus leaked information about her, if she shares her data. Whereas here, we see that she doesn't share her data, she doesn't get the payment, but the leaked information has 0 here rather than 1. And in all of this, of course, A minus I is taken as given. So yeah, you see the same thing, convention as in the example is being adopted here. The value of information for the platform is normalized to 1. The value of privacy in the same units is VI for user I. So once you specify this model, analyzing it is not that hard. We define a user equilibrium. So given a price vector, an action profile of the user equilibrium, if every user chooses the optimizing data sharing decision given the action profile of others. So that defines a set of user equilibria at a given price vector. And then we look at the Stackelberg-like equilibrium concept, where a pair PEAE is a pure strategy Stackelberg equilibrium if there is no profitable deviation for the platform, such that by choosing a different combination of prices and action profiles within the set of user equilibria, the platform cannot make greater profit. So this Stackelberg equilibrium in the usual Stackelberg fashion gives quite a bit power to the monopoly platform. In particular, I get to choose both the price and one of the equilibria in the set of user equilibria. You could modify that to a weak Stackelberg equilibrium where there's a different selection in the set of user equilibria, but it doesn't really matter for most of what I'm going to say here.
Daron, can I ask a question?
Of course, please, yes.
Yeah, so the price that you can offer a user to share their data cannot depend upon the actions of other users.
Right, so that's a very important question. Thank you for clarifying that. So I'm assuming that here I'm not offering conditional prices. So we could go one step forward, which of course is not the practice right now, but you could try to do something where I will offer you more for your data if simultaneously Marina decides not to share her data or something like that. So we could definitely look at more generalized price mechanisms of that sort. That's a good question. But no, so here the timing of events is I offer a price vector that's unconditional, and then given that price vector, people play the game.
Thanks.
Right. Just for future reference, let's also specify utilitarian social welfare. That's natural. That's 1 minus VI times leaked information. And then the first best is the one that maximizes utilitarian social welfare. Now, you may have very reasonable objections to utilitarian social welfare. It values the platform surplus the same as individuals, so distributional concepts. But even with this, we're going to have some interesting inefficiency issues, which I'm going to talk about, and then distributional concerns can be incorporated. And the first best is actually sort of not as simple an object here for the very simple reason that in the presence of these externalities, it may well be that Marina, for example, shouldn't share her data, even though her data is very valuable to me, because she will reveal information about somebody else. Or conversely, for example, Tillman should share his data, even though his privacy is very valuable, because he will reveal information about other people whose privacy is not that valuable, and that information that he reveals about others is socially valuable. So that's what this characterization here takes those things into account. That's why you have the covariance structure of everybody's data together in here. But there's one simple case, which is a useful benchmark to bear in mind, of course trivial, but still useful to bear in mind. If there's no correlation, if those covariance terms are all 0, only the covariance with yourself is 1, then, or sigma square, sorry, sigma I square, then all users with VI should share their data, and all of those with VI greater than 1 should not. All right. So now we come to the key lemma that's going to play a role in the analysis that comes. We show that the leaked information measure that I talked about is monotonic, which means more information is revealed when more people share their data. And moreover, it's submodular, which means that the additional information that you will reveal yourself is lower when other people are sharing more. So submodularity makes a lot of sense, but it's not universal. So you can come up with measures of different measures of leaked information and different covariance structures, not normal, where submodularity may fail, but it is satisfied for many reasonable, for the general set of things, including things that are based on mutual information entropy like objects. And in a second, I will show you that all of the results that I'm presenting first for this normal setup are going to generalize as long as you have monotonicity and submodularity. So in some sense, this normal setup is a vehicle for transparently communicating the implications of monotonicity and submodularity. The rest of the analysis is pretty straightforward, and since time is short, let me go a little bit fast here. So this, for any price, the set of AP, the set of user equilibria, is a complete lattice. So that makes analysis a little bit simpler. And then an equilibrium, a Stackelberg equilibrium, always exists. And even if there are multiple equilibria, because of this power of the Stackelberg leader monopoly platform, they all yield the same profit to the platform. Now, before I jump onto what prices look like, which I'm going to do briefly, I want to show you that there are natural non-monotonicities in this model. And to do that, and also reveal one of the forces that will play an important role in the inefficiency in a second, let's take the following example. Again, let's pick two users. Now let's have both users have the same valuation of privacy V. And again, the correlation between the two is rho, and their variances is 1. And let's compute here what the total payments to users will be in this Stackelberg equilibrium as a function of V. And what that looks like is this. So as I increase V, that's the surplus. Sorry, I want to show first the payment, sorry. The total payment. So the total payment to induce both users to share is V times 2 minus rho squared over 4 minus rho squared. The reason why rho squared comes in here is that the thought experiment, when I'm getting both users to share it, the other user is already sharing. What do I need to pay you so that you share? But what that means is that the rho part of your information is already revealed, so you don't get compensated for that. So I, as the Stackelberg leader, can offer you a reservation price, which is now lowered because of that rho. So that's the submodularity. If, on the other hand, I only want one user to share, what do I need to pay her? Well, I need to pay her V over 2. Now the rho is not there because the other user isn't sharing. All I need to do is convince you to share your information. Now you see that one aspect of non-monotonicity here is with respect to rho. When rho is high, so rho square is greater than 0.71, the platform pays less to have both users share their data. Why is that? Well, that's the same intuition as the example in the introduction. When the two users are highly correlated, then when I'm trying to convince you to share while the other user is already shared, then I don't need to pay you much. So I can get both users to share for cheaper than a single user sharing. So that's the aspect that really, I think, brings home some of the ideas here. For the same reason, surplus here is non-monotonic in V, privacy. When privacy is very, very high, here greater than 4 divided by 2 minus rho square, then nobody will share. Then you get 0 surplus. If privacy value is less than 1, then both users share. And the platform doesn't need to pay all that much because of the thing that I've just explained. But that's a distributional issue. The surplus doesn't care who gets the benefits. So the total surplus is positive. So we have something above 1. But here is the interesting segment here. When the value of the users is between 1 and this higher threshold, both users still share because of this Bertrand competition between them. But even though they share, they are both worse off and the platform benefits hugely and total surplus is negative. What's going on here is that each user is forced to share because the other one is expected to share, and therefore my data is not very valuable, again, the depressed prices. Now, the general characterization for prices, which is in this theorem, which is in terms of the variance covariance, but it takes a rather simple form given here, brings this point home. Given that time is short and I want to sort of leave time for questions at the end, let me not dwell on the exact expression here, except for making 2 points. One is that it's very easy to derive this expression from a decomposition of the covariance matrix, and it's really sort of the conditional expectations that's really the relevant object here. But the second is more conceptual. It's already obvious to most of you, but let me repeat it. The prices in this model are just the reservation values for individuals to maintain or sell their data, and the reason for that being, again, the Stackelberg position of the platform. Now, at this point, you can ask, well, perhaps we don't have a Stackelberg set up. Perhaps it's more like a bargaining, etc. That would lead to different results. But I think given the asymmetry of power there is between data companies and platforms and users, the Stackelberg is a pretty good starting point, in our opinion. All right. Now, let me come to the key efficiency results. And then I'll talk a little bit about the generalization, competition, and then regulation. I will conclude. So let me first present this trivial lemma, which says that all low-value users, where I'm defining low-value users as those whose valuation is less than or equal to 1, will always share their data in equilibrium. This is trivial except for those who have value 1, and you can establish the one that those with value 1 will also always share. Of course, they get a private benefit. Regardless of what other people are doing, they're going to share. Then what about the high-value users? Those are the ones whose valuation is greater than 1. They may or may not share. I've already shown you in this example here that high-value users might share as well. We just will depend on the exact equilibrium, depending on the covariance structures, etc. And for future reference, let V superscript H be the vector of high-value users and V superscript L be the vector of valuations of low values. So here is the main inefficiency characterization. If all high-value users each high-value user is uncorrelated with all other users, the equilibrium is efficient. If, on the other hand, at least one high-value user is correlated with a low-value users, with at least one low-value users, then there exists a V bar such that if the valuations are now less than V bar, the equilibrium is always inefficient. This second part is therefore about correlation between high-value and low-value users. Inefficiency depends on the data externalities. Of course, the nature and magnitude of the inefficiency, as I will comment in a second again, interplays with the depressed prices, and it can get much magnified for that reason. But at the root here is this data externality. Low-value users are sharing. They're creating this negative externality. Why do we need this VH greater than V bar? Well, because if VH is very, very low itself, so the high-value users have valuation 1 plus epsilon, then it may be socially optimal for them to share it for the benefit that they generate for the low-value users. It's an unlikely case, but to get it into a theorem format, you need this condition. The third part is the complementary case. Now, high-value users are uncorrelated with low-value users, but they are correlated among themselves. So high-value users are correlated with at least one other high-value user. Then there exists a V bar I such that if VI is less than V bar I, the equilibrium is inefficient. And this inefficiency is largely about depressed prices. So it's really this case here, that the two high-value users are correlated and they depress each other's prices, and neither of them really would like to share, but they both end up sharing. Now, at this point, you might say, well, this is a very complex game. Efficiency is not a reasonable criterion. It might be inefficient to have the equilibrium, but data is still very useful. That's definitely a reasonable perspective. But as one step of the argument beyond this perspective, we can also look at whether overall data markets are beneficial. So to do that, in general, is not straightforward, but we can have a general bound on the social surplus from data sharing, and it's given here. And it's a bound rather than exact, because the first term here is the benefits are an overstatement of the benefits, and the second term, the costs, are an understatement of the cost. Why? Because the benefits I evaluate suppose that everybody shares the data that's relevant about low-value users for whom data transactions are useful. And here, I understate the cost because I assume that only low-value users share, whereas the example I showed you is that you might get additional inefficiency from high-value users sharing. So, but once you have this bound, it's pretty straightforward that it is easy to construct cases where utilitarian welfare improves when data markets are completely shut down. Again, it's an extreme case. We're not advocating in this paper that data markets be shut down, but it's easy to construct such cases, or at least for some subsets of certain types of data, it may be that social surplus is negative. And here is an example, which I'm going to skip going into the details. It's very easy to construct examples where data markets are generating negative externalities. So here is one with an island structure. Each island is a low-value island and a high-value island. And then depending on the correlation and the value of the privacies of the high-value users, this whole purple area is where negative social surplus. Now, at this point, many of you may be wondering whether these conclusions are general, in particular normal distribution correlations and specific value of mean square error are specific and may not capture much of what we want to capture in terms of representation of the types of users of data. So here is a generalization, which I'll give very quickly. And let me list these 4 properties. The first one says, if user I's information is independent from the information of all other users, then there is no leakage. The second property says leakage with non-dependence, which means that if the information of 2 users are not independent, then there will be some leakage. And the third property is a general monotonicity properties, which is something we proved a second ago with the lemma. The fourth one is a submodularity. So what I introduced early on with the normal, specific, mean square error, etc., satisfies all of these properties. Independence is equivalent to lack of correlation in the normal case. And here is a theorem which is identical to the inefficiency theorem I showed a second ago, except that now it's for the general case, assume these 4 properties hold. And then instead of uncorrelated, we use, of course, independent. That's it. Other than that, it's exactly the same result. So this is just underscoring what I said. Really, all of the results depend on monotonicity and submodularity. This no leakage with independence and leakage with non-independence are, of course, natural. They're just sort of give you some meaning to the payoff functions. One other issue that you may worry about is that all of the results so far were under the assumption that the platform, though doesn't know the relevant information about users, knows the correlation structure. That is a very strong assumption. Generally, platforms learn the correlation structure from the data that they get as well. So we generalize these results so that the correlation structure itself is incomplete information, and then the same result holds exactly. Now all you require is that the correlation structure itself puts positive probability on the events that led to the inefficiency. So time is running short. So let me be brief on the competition. Obviously, a framework that has a monopoly platform is problematic for being a representation of reality, but it's also more potentially problematic from a theory point of view, because competition might actually endogenously generate solutions to the inefficiency. And essentially what we show is that that's not true in general. And we look at 2 different types of competition, either one in which platforms first offer prices, or one in which individuals first join platform and then platforms offer you goods and services to buy your information. But in neither case, competition resolves inefficiency. And the best way of seeing that is not give you the theorem, since there is not much time, but give you an example. take this example that I went through already, and suppose V1 is less than 1, and now compare a situation of competition between two platforms versus one in which there's a monopoly platform. Now, if V2 is very high, greater than 1, then competition may improve economic surplus. Why is that? Well, in this situation, you can have that individual 1 joins first platform, individual 2 joins second platform. And if there is limited leakage between the two platforms of information, Twitter cannot get the information from Facebook, then this actually protects player 2. But now imagine that V2 is actually less than 1. Now there's a distributional reason for individual 2 to go to platform 2, because if she goes to platform 1, still, even though it's efficient for platform 1 to get the information of both users, that correlation structure and depression of prices that I've pointed out will imply that player 2 is going to have a low reservation value, so won't get much of the surplus. So as a result, she will have a reason for going to the second platform, but in this case, V1 and V2 are less than 1, so it would have been better for both of them to be on the same platform. So there's no presumption that competition will improve efficiency here, and we characterize that and do that. So let me end in 1 minute by talking about, if there are these data externalities and inefficiencies, what can you do about them? Obviously, if the social planner knows everything, she can have personalized taxes on data transactions, and that could just restore the first best. Trivial. But we also show that if you are forced to have uniform taxes or uniform regulations, you cannot do that in general. So it's not a trivial problem to solve these inefficiencies. So the final thing that I'm going to do is a little bit of a wild idea that we end the paper with, which is, what if we use mediated data sharing arrangements that try to deal with this issue? And again, here, the critical point that I made at the beginning, that the problem here is not anonymization. So it turns out that one thing that might work here is what we call decorrelation. If there is a trusted party, then everybody can share their information with the trusted party, and the trusted party can then take linear transformations of that data, which means that in practice, of course, mathematically, that's clear what that means. But in practice, what that would mean is that Mariana and I both share our data. Mariana doesn't want Facebook to know her data, but some of my data is informative about Mariana. So we garble that part of my information. So in this normal setting, that's very easy. You don't just construct a new data as tilde, inverse of the variance covariance matrix times S. And the beautiful thing about this is that if Mariana doesn't want to share her data, that any shared data has zero correlation with her true information. So mediated, if there is indeed a trusted party that people can trust, then some of this problem at least would have a partial solution. And then we show that with this mediated decorrelation device, you can improve social surplus. You may not always reach the first best, but you always improve social surplus. And most importantly, you can never anymore have a situation in which data markets lead to negative surplus. Why is that? Because the negative surplus always comes from somebody like Mariana having her information revealed when she doesn't want it. But with this decorrelation measure, anybody who wants to opt out of Facebook will have none of their information, all of their information being garbled through other people's data. Anyway, let me conclude there and take some questions. This is part of a broader research. We have other projects looking at some of these issues. So certainly questions and comments are more than welcome. Thank you.
Thank you so much, Daron. That's wonderful. So I see that Pradeep has a question.
Mine is a little tangential to your talk, but if we factor in the money made by platforms and how that is plowed back into society in many ways, employing people, doing more research, how does that impact inefficiency notions?
So the measure that I've used, Pradeep, does have the value of the platform completely taken into account.
I see. Okay.
So I'm looking at the inclusive measure. In fact, you might go the other way. So it's what's going on here is that data markets are doing two things, and that's very interesting. And we just went for the more conservative notion. They are first reallocating surplus from users to platforms because of these depressed prices.
Mm-hmm.
And then they're also creating the negative externalities. So to be more conservative, we took all of the surplus of the platform and added that to the utilitarian social welfare. But you might say, actually, because we don't like Facebook and Google to capture all of the surplus in society, even though some of it is being plowed back, we should use a weighted surplus, and that would make the inefficiencies much worse here. Thank you.
Thank you.
I don't know if there are other questions here. There have been some interesting discussions in the Q&A, so maybe we can have you, Daron, comment on some of those. And Ali and Azaraq, if you also want to tell us what you found interesting. I see there is a question that Ali has suggested that we bring up to you. It's a question by Hesky Barisak. He says, this is not a question about the model, rather its implications here for some parameters, the interesting ones. If users could coordinate, they would prefer to institute a ban on information gathering. Do you think if we polled users in practice, they would be in favor of doing so?
That's a great question. So absolutely right. So in fact, any coordination between users, any free coordination between users, either through institutional means or other means, would get rid of the second inefficiency, part 3 of the theorem. Because there, the inefficiency is taking the form of, say, Azaraq and I are correlated, and we both get squeezed via the Bertrand competition logic in sharing our data. Now, the problem about that is that if you ask individuals in surveys, A, I don't know whether that's an easy question to ask, and B, who will be part of that arrangement? So you could ask that for me and Azaraq together, but perhaps there are 3 or 4 other people who are already sharing our data. So in the logic of the model, you need that to be together for all individuals who are correlated. And that may not be easy, but that's a very good question, Hesky. Thank you.
Wonderful. And I see that we have also some discussion here on the use of Kramer-Marklin type of mechanisms, whether they could be optimal if you were to allow for a more general type space of mechanisms.
That's a very good question. So in the paper, we also look at the case in which the user valuation is incomplete. And then you have the mechanisms. But one could go one step further, and that's essentially what Navin was also asking about. We could also try to have mechanisms on the data realizations. We haven't explored those, and I think that's definitely a very good area to think about. Okay,
very good. So I guess one question I will ask you, so thinking about these settings with externalities, whether there are going to be situations where we face the problem of multiple equilibria, and whether we want to think of unique implementation mechanisms.
Perfect. I think that's great. So that's exactly, we've also, as I said, we're leaving a lot of questions for the future. Our use of the Stackelberg equilibrium is essentially cutting through some of the multiple equilibria.
Yeah.
Now, multiple equilibria here actually is not that bad. So multiple equilibria could sometimes be a defense mechanism. So somehow if Azaraq and I are correlated and we somehow use the right equilibrium selection so that we both don't share, that could be an equilibrium also. Now, but the question is, how do you do that correlation? What's the right equilibrium selection device? So to us, it seemed like, given that there is a platform with huge asymmetric power, to start from the case where they have the equilibrium selection is in their favor made sense, but obviously we need to do more on that one as well.
That's excellent. Thank you so much, Daron.